Alright, another topic that is of interest to the exam, I think it was covered maybe in chapter 6, that involves reaction coordinates. Everyone knows and loves those. There's something that looks reminiscent of, that reaction. It's usually how they're referred. You have your E for your energy over there. Also, sometimes maybe they're, got a couple steps in them there as well. What these are, they're kind of showing the energy during a reaction and the steps. So there's a couple things of interest that could pop up on your exam pertaining to these. We'll talk about each one, hopefully, or at least most of them. So let's talk first about this reaction coordinate. So we'll name it. We'll have our energy over here. Let's say, so we start down there, go up, and we go right there. So if this is our reaction coordinate, we have to tell a couple things. First, let's determine, is it sn1 or is it an sn2 reaction? So looking at it, you can see, well, it goes up one hump and it goes down. So that tells you probably, in most cases, there's going to be one step that happens here. One step means what? sn1? No. sn1, remember, has two steps. The leaving group leaves, and then, so for example, we'll say Br. So Br would leave. This would render us with a carbocation, right? So that would be our one step. This would be our intermediate, and then up would come our nucleophile that would attack, I don't know, whatever, OH, and it would come in and attack there, and then we would have our final product. But let's not get too carried away right now with the actual reactions. Let's focus on our coordinates. So we just determined that this single hump was actually going to be a sn2, right? Single step reaction. So what is going on here? Let's see. Well, we start down here. This is going to be our reactants, right? And we're going to be looking at this in the forward direction. We'll come back later and say, oh, the reverse direction of the reaction, let's go that way. But forward direction. So starting down here, this is going to be our reactants. And it would make sense then for this over here to be our products, right? Alright, so what's this up here? So reactants, products, question mark, what's happening? Well, it makes sense to think that this is our transition state, or intermediates for other type of problems. For SN2, it's typically referred to as a transition state, which is drawn on in the form of brackets with this funny little symbol out there, and then you draw the molecule in here. Typically the construct is, to have dashed lines to show the breaking and building of bonds simultaneously. So up here, as we just said, would be our transition state for our SN2 reactions. What else can we tell about this? Is it endothermic or exothermic? Well, the way to tell that is by looking at the level by which the products are compared to our level of reactants. So we see our reactants started way down here on energy, and they finished up here with our energy, right? Following the hump. So our products essentially absorbed energy during this reaction. They ended up being a higher energy product. So this would be endothermic, right? If this was down here, way down here, and it was lower, it would be the inverse. It would be exothermic. We'll do an example later. What is this region called, this region that I just dashed in right here? Typically, you'll label it as delta H. If I remember, that's your change in enthalpy, I believe. So yeah, you double check that with your notes in your book, but I know it's delta H. So what about another important structure on here, from up here at the very tippy top to our first hump all the way down to our original reactants here? That's typically called, I'll draw a line with an arrow pointing to it, that's typically called our EA, which is also known as our activation energy. A for activation, E for energy. This is the amount of energy that it takes to get to our transition state. Once we surpass that transition state, the reaction's going to complete and go all the way to the products. Let's see, a interesting type of way to look at this also, as we just said maybe a couple minutes ago, is the reverse, because some reactions you may be familiar, instead of just having a single arrow, sometimes they have this type of equilibrium type arrow, so they can go forward or the reaction could go backwards. With this coordinate we just did, we looked at it in the forward direction, right? So you could go in the reverse reaction, where it would go, this would be our reactants, and then this would be our products. So let's look at it from that direction. So same one, very close to what we drew up there. We're going to be looking for the reverse reaction. So we're going to start up here and finish down there. This is now our reactant side, this is now our product side. You'll notice that this is still, we'll just put some brackets there with our symbol, that's still our transition state. An important thing to keep in mind now, though, is our activation energy is a lot lower. It's only from there to there. It's no longer, see up here, it was almost the length of my marker. Here, it's just the tip of the marker. It's a lot easier in this case to do the reverse reaction. It takes a lot less energy to get activated to that transition state. How about this reaction overall? Would this one be exothermic or endothermic? So you could look at it a couple ways. You could use your reasoning and say, oh, well, the reverse of an endothermic reaction is probably going to be exothermic. Or you could just look at the graph and do the little dotted structure again and say, oh, well, the products are lower in energy than where they started. That must mean energy was given off from the molecules, so we end up with exothermic, if I can remember how to spell. Alright, so what else do we have here? So this was sn2, correct? And not very often when you talk about sn2 are you going to be talking about these reverse directions. That's just, I guess, kind of more for your general knowledge. But let's look at sn1 right now. So let's see, we have another reaction coordinate. You'll notice that this one we'll say like that. Alright, so we have something that looks a little bit different than what we had before, which is a single hump. You'll notice now there's two humps. So that kind of makes sense as to mean there's two steps. And you could deduce from that, well, then we're probably talking about, in this case, an sn1 reaction with two steps. So again, we can tell a few things right off the bat. One, that looking at our change in H, or delta H, that this is going to be a exothermic overall, right? Because we're way down here compared to up here, so our energy is lowered. Where's our rate determining step here? Well, you may remember from your notes right off the bat that the first step is our rate determining step in SN1, where the leaving group leaves, but you can also tell by simply looking and getting a hint from the chart which one requires more energy to achieve. From going from here to there, which means we need an activation energy all the way up to there, or going from our intermediate, which is what this is. Let's just call it inner for intermediate. This is where in SN1 we're going to have our we'll just put a C with a plus. This is where our carbocation, which remember we drew earlier, plus charge. This is where this is formed, our intermediate, right there at that little lower divot that forms. So which one returning back has, what would you say, the slower process, one that requires energy to go all the way up here from down here, our initial reactants, or for our intermediates to simply go up to that little amount. Very little rabbit slope compared to this steep mountain right there. So we could, use our reasoning again and say that this one that requires a lot more energy, this first hump is going to be our rate determining step, and that agrees with what we know, as we just said. SN1's rate determining step is the first step. So I think that was, again, remember we have transition states. Now we have two transition states, one for each respective peak. Again, it's important to remember that these are not the intermediates, that down here is our intermediate product. These are the transition states, which don't, you couldn't extract these and hold them in your hand by themselves. They're just, kind of like something that theoretically exists and happens very fast. It's something that can be isolated, the transition states. Intermediates are a different case. Sometimes they can, sometimes maybe they can't. But in all, what would you say, reasonings for this test and exam, consider this one to be probably more stable than the transition states. And our products for this curve, for this coordinate, is the most stable at all, with our lower set of energy. I think that is maybe the gist of what we need to know. Exothermic, we talked about endothermic, reverse reactions, forward reactions, and our two-type SN1, SN2. Offhand, I think that should be about it. Be comfortable in case you have to draw one of these type of constructs. Know where the intermediates are, which one has intermediates, which ones have transition states. There's a hint they both have transition states, and how to label them. For example, remember from here down to here, so we'll draw a line. That is our delta H, and remember, from our starting to our top, that's our activation energy. This one also has activation energy just for that little tiny rabbit hole right there. So again, all important stuff, but all makes sense if you just sit and think about it for a little while.